In this video, we will see further different forms of equation of a plane with different conditions. The first condition in this video that we would see is there are three non-collinear points of the plane which are given to us. Then we are going to find the equation of the plane. According to the theorem given here, to find the parametric form of a vector equation with three collinear points of the plane, if three non-collinear points with position vectors a, b, c are given, then the vector equation of the plane passing through the given points in parametric form is given by this formula, where your vector b is not equal to 0, vector c is not equal to 0, and your s and t belong to real numbers. Let's consider three non-collinear points a, b, and c. So, a, b, and c are non-collinear points, and let a vector be equal to the position vector OA and b vector equal to the position vector OB and c vector the position vector of OC. Further, let P be a point on the plane and R vector be the position vector of the point P. Now take a point D such that D is on AB. It can be produced, which means it's not within AB, maybe it's extended, and AD vector is perpendicular to DP vector. So our AD vector can be defined as a scalar quantity S times B vector minus A vector, which is our B minus A vector is nothing but the vector AB, and since AD is parallel to AB, we can define AD as a scalar S times AB vector, which is B minus A vector, and similarly our DP vector can be defined as T times C vector minus A vector. That's because we should add another condition here, which is our DP vector is parallel to AC vector. Further, in triangle ADP, we can say that the vector AP is equal to AD vector plus DP vector. So substituting the values correspondingly, we can rewrite this as R minus A vector, which is AP vector, is equal to AD, which is defined as S into B minus A vector, and DP is T into C minus A vector. So moving the A vector to the other side, you can write this as R vector is equal to A vector plus S into B minus A vector plus T into C minus A vector. So that's the proof of this theorem. Next, let's find the non-parametric form of vector equation. So we have the parametric form here. Now let's find the non-parametric form. So for the non-parametric form, let's again consider the points A, B, and C as collinear points, and let vector A equals OA vector, and B vector is equal to OB vector, and C vector is equal to OC vector, and R be the position vector of any point P, so that's equal to OP vector. So we can define our AB as B vector minus A vector and our AC vector as C vector minus A vector. So we have AB and AC vectors on the same plane, and we also know that A, B and C are non-collinear, and further AB vector is not parallel to AC vector. Therefore, we can say that our AB vector cross product with AC vector is perpendicular to the plane, which implies AB is B minus A vector cross product with C minus A vector is perpendicular to the plane. Our AP vector, which is nothing but R minus A, is on the plane, therefore it is perpendicular to our B minus A cross product with C minus A vector. Therefore, we can say that the scalar triple product, which is R minus A dot product with B minus A cross product with C minus A is equal to 0, and that's our required proof. Now for the Cartesian form of the equation. Now if we consider our points A, B, C as x1, y1, z1, x2, y2, z2 and x3, y3, z3 respectively with the position vectors A, B and C, then let x, y and z be the coordinate of the point P with the position vector R. So now our vector A can be defined as, this is our point and this is the vector A, which position vector, so it's equal to x1 i cap plus y1 j cap plus z1 k cap. Similarly, B vector will be x2 i cap plus y2 j cap plus z2 k cap, and C vector here will be equal to this point C here, which is x1 i cap plus y3 j cap plus z3 k cap, and our vector R, which is the position vector of P, will be defined since x, y and z or the point is the point. We will have R vector is equal to x I cap plus y j cap plus z k cap. Now we know that in the non-parametric form this was the equation. So replacing our vectors R, A, B and C into this equation, we can say that this is a scalar triple product. Substituting the values which are the coefficients of x I cap, j cap, k cap for A vector, B vector, C vector and R, and expressing in the determinant form, then we can rewrite this equation as this determinant equals 0. So that's the Cartesian form of equation. The next scenario that we'll be looking at is how to find the equation of the plane when you're given a point of the plane and two non-parallel lines or non-parallel vectors which are parallel to the plane. So the two vectors that you have, they are non-parallel, or they are lines and they are not non-parallel, but they are parallel to the plane, and you're also given a point of the plane. So the parametric form of vector equation in such a condition is, consider a plane passing through a given point A. So the point that we talk about here is A with the position vector A, and parallel to two given non-parallel vectors B and C. So B and C are our non-parallel vectors. If our vector is the position vector of the arbitrary point P on the plane, then the equation of the plane can be described as A vector plus SB vector plus TC vector, where our S and T are, they belong to real numbers, they are scalar quantities. Further, in such a condition, the non-parametric form of the vector equation is given by R minus A dot product with B cross product with C equals 0. Further, the Cartesian form of equation for such given condition can be obtained by rearranging the non-parametric form, where A vector is defined as x1 I cap plus y1 j cap plus z1 k cap. This is given to us. And vector B is defined as b1 j cap, b2 j cap and b3 k cap. Again, this is provided to us. And vector C is defined as c1 I cap plus c2 j cap plus c3 k cap. Again, this is provided for us. So this is what we assume the point P, which is R is equal to x I cap plus y j cap plus z k cap. Then rearranging this scalar triple product, we can get this determinant equals 0. That's the Cartesian form of equation. The third condition for obtaining the equation of the plane we would see in this video is, you're provided two distinct points of the plane. So you're given 2 points on the plane. We can call it as A and B, and a straight line or non-zero vector parallel to the plane but not parallel to the line joining the 2 points. So the non-zero vector is parallel to the plane, but if you connect these 2 points AB, then it's an AB vector, and this vector is not parallel to this line, which is non-zero vector, which is provided to us. So we have 2 points on the plane, and we have a vector which is parallel to the plane, but it's not parallel to the line which joins these 2 points. So the parametric form of such a condition can be obtained. The parametric form of vector equation of the plane passing through 2 given distinct points A and B with position vectors A and B and parallel to non-zero vector C is, or vector is equal to, or is the position vector of any point P, is equal to A vector plus S times B minus A vector, where S is a scalar quantity and it's plus T C vector. Again, T is a scalar quantity, or you can rearrange this formula as R vector is equal to 1 minus S A vector plus S B vector plus T C vector, where S T belong to R and B minus A and C vector are not parallel vectors. And this equation can be written in the non-parametric form of equations as R minus A dot product with, just by moving the A to the other side, becomes R minus A, and also we know that this 2 B minus A cross product with C vector will be perpendicular to the plane. So dot product with R minus A, which is on the plane, will be equal to 0, and B minus A and C are non-parallel vectors. Further, rearranging this formula with vector A as x1 y1 j x1 I cap plus y1 j cap plus z1 k cap, and B as this and C as this, and our R vector, the position vector of any point P, as this, then we can rewrite this scalar triple product as the determinant value of this, which is equal to 0. So this is the Cartesian form of equation.
Thank you for watching Maths Tutorial Anand. Please like, and you can comment if you have any questions, and do not forget to subscribe to get more videos like this.